Published in 1988, A Brief History of Time by renowned physicist Stephen Hawking aims to elucidate complex scientific concepts like space, time, gravity, black holes, the Big Bang, and the expanding universe for general audiences without expertise in advanced physics or math. In this 11-chapter book, Hawking discusses profound questions that have long perplexed scientists regarding the origins, evolution, and fate of the universe. He interweaves pivotal discoveries and theories in physics over the past 3 centuries in a cohesive narrative about humanity's quest to understand the fundamental mechanics of reality. Writing with wit and accessibility, Hawking renders abstruse ideas from relativity, quantum theory, thermodynamics, and cosmology intelligible to lay readers. The central lesson is that the cosmos operates rationally according to elegant mathematical laws which physicists seek to discover through observation, reasoning, and imagination. This popular science classic dispels mysticism around physics, arguing that its basic tenets and our place in the universe can be grasped by anyone. Chapter 1. Our Picture of the Universe. Hawking opens by contrasting outdated geocentric and heliocentric models of the solar system with our modern understanding of the universe derived from centuries of astronomical observations and physics experiments. He explains how Copernicus, Galileo, and Newton gradually replaced an Earth-centered model with a vision of a stable, infinite universe of stars centered around the Sun. However, in the 1920s, Edwin Hubble discovered galaxies outside the Milky Way retreating rapidly away from us. This contradicted the notion of a static, unchanging cosmos. It implied an expanding universe that originated billions of years ago in a massive explosion, the Big Bang. Hawking reviews evidence like cosmic microwave background radiation supporting the Big Bang theory. He previews how particle physics and relativity theory will shed light on conditions movements after the Big Bang, while quantum effects govern behavior inside black holes. Chapter 2. Space and Time. Hawking delves into Einstein's special and general theories of relativity, which revolutionized our concepts of space, time, mass, energy, and gravity. He unpacks Einstein's Gedanken experiments, imagining what observers would see from inside accelerating elevators or speeding trains. This reveals that motion is relative. There are no privileged inertial frames. Whether something is at rest or moving depends on your frame of reference. More disturbingly, time passes slower for objects moving rapidly relative to you. Hawking explains Einstein's formulas quantifying time dilation and length contraction. He also covers how gravity warps space-time itself, rather than being a traditional force. Hawking shows how relativity merged space and time into a 4-dimensional space-time fabric that can stretch and curve. Spatial distances and time intervals are not fixed, but depend on an object's speed and the gravity acting on it. Chapter 3. The Expanding Universe. Hawking chronicles empirical findings in the early 20th century that contradicted the assumption of a static, eternal universe. Westo's Slipher showed galaxies outside the Milky Way were systematically redshifted, implying they were receding away at high velocities. Hawking details Edwin Hubble's pivotal observations, definitively proving we inhabit an expanding universe. Hubble studied Cepheid variables in Andromeda to calculate its distance, showing it was a galaxy outside the Milky Way. Moreover, Hubble formulated a linear law showing more distant galaxies recede faster. Hawking explains the Big Bang theory emerged from extrapolating this expansion backwards like rewinding film. All matter originated from an extremely hot, dense initial state 13.7 billion years ago that inflated rapidly in the Big Bang. Hawking discusses evidence for the Big Bang, like the cosmic microwave background radiation, and expanding universe accords with relativity theory, which permits space itself to stretch. Chapter 4. The Uncertainty Principle. Hawking delves into quantum mechanics, which governs behavior in the subatomic realm. He contrasts Einstein's deterministic mechanical view of physics with quantum randomness and inherent uncertainty in measuring complementary properties like position, momentum, or time energy. Hawking unpacks Werner Heisenberg's famous uncertainty principle, which places quantitative limits on how precisely one can know a particle's properties simultaneously. Quantum particles lack fixed attributes until measured. Hawking elucidates Erwin Schrödinger's thought experiment, imagining a cat that is simultaneously dead and alive inside a box until observed. This highlights the bizarre implications of quantum superpositions and wave-particle duality. Measurements induce collapse of the wave function. Hawking explains how the probabilities of quantum outcomes accord with the amplitude of waves or wave function. Though a counterintuitive quantum theory makes astonishingly accurate predictions confirmed repeatedly. Chapter 5. Elementary Particles and Forces of Nature. Hawking surveys the miniature of fundamental particles physicists have identified using atom smashers to resolve matter's basic constituents. The universe comprises various quarks, leptons, and bosons that interact through four fundamental forces: gravitation, electromagnetism, strong nuclear, and weak nuclear forces. Hawking chronicles efforts like the quark model to classify hundreds of unstable, short-lived subatomic particles into orderly families sharing common properties and governed by symmetry principles. He explains how quantum thermodynamics binds quarks into protons and neutrons through color charge. Particle physicists seek an elusive theory of everything, uniting all forces. Hawking discusses efforts to link three forces through grand unified theories and supersymmetry. This raises hope of deducing universal laws, explaining all physical phenomena from first principles. Chapter 6. Black Holes. Hawking tackles the mystifying consequences of gravity becoming extremely intense. When massive stars exhaust their nuclear fuel, core collapse can form a singularity, a point of infinite density and space-time curvature. The intense gravity of this black hole warps space-time so severely that nothing can escape, not even light. Hawking explains how black holes are surrounded by an event horizon delineating their boundary. He details research into black holes by Carl Schwarzschild, Robert Oppenheimer, John Wheeler, and others. Relativity theory allows black holes but precludes observers from witnessing the singularity. Hawking calculates the unimaginably extreme gravity near black holes, which can spectrify objects. He describes theorized primordial mini-black holes formed after the Big Bang and the prospect of detecting Hawking radiation from their quantum evaporation. Chapter 7. Black holes ain't so black. Hawking delves deeper into black hole thermodynamics, building on work by Jacob Bekenstein. He explains how black holes have entropy proportional to their surface area, which increases when matter or radiation is absorbed. Counterintuitively, black holes radiate energy and ultimately evaporate away at a temperature inversely related to their mass. Smaller black holes emit more intensely than larger ones. Hawking radiation arises due to fluctuating virtual particle pairs around a black hole's event horizon. One particle may fall in, causing the black hole to lose mass energy while the partner escapes as radiation. Thus, black holes are not eternally black, but actually glow faintly and slowly shrink over eons by converting mass into radiant energy according to E is equals to mc squared. However, for stellar mass black holes, evaporation takes far longer than the universe's current age. Chapter 8. The Origin and Fate of the Universe. Hawking explicates how the initial conditions and evolution of our universe can be explained scientifically within the context of space-time, according to general relativity theory. Extrapolating the expanding universe backwards implies a hot Big Bang origin. However, relativity theory breakdowns at the immense densities reached as the universe approaches a gravitational singularity. Hawking discusses how quantum fluctuations could drive a spontaneous inflationary expansion movement after the Big Bang that smoothed out microscopic inhomogeneities to explain the observed large-scale uniformity of matter and temperature throughout space. He then covers three proposed fates of our universe: endless expansion, collapsing back in a big crunch, or hitting a steady state. Which scenario unfolds depends on the total mass energy density, which determines the curvature of space-time. Deducing the universe's mass density from observations of its expansion rate remains an active area of cosmology. Chapter 9. The Arrow of Time. Hawking grapples with the unidirectional flow of time which seems built into the fabric of reality. The second law of thermodynamics dictates that entropy or disorder always increases in closed systems as heat dissipates and structures break down irreversibly over time. Hawking notes how thermodynamics aligns our psychological perception of time's arrow with its physical direction in macroscopic processes. However, the fundamental microscopic laws of physics, like relativity and quantum theory, are essentially time reversible. So what makes time's arrow point only forward? Hawking discusses possibly cosmological explanations rooted in the conditions after the Big Bang set a low entropy initial state from which entropy could rise thereafter. Alternatively, the arrow of time might emerge from quantum uncertainty or complex interactions between many particles that amplify microscopic irreversible effects to the macro scale. Chapter 10: Wormholes and Time Travel. Hawking analyzes speculative ideas at the frontiers of research like wormholes and time machines permitted by exotic solutions to Einstein's equations. Wormholes are hypothetical tunnels through warp time-space that could act as cosmic shortcuts through space. While possible, mathematically stabilizing them would require exotic matter with negative energy density. Hawking considers whether time travel could be achieved by entering one mouth of a wormhole in the future and emerging from the other mouth in the past. However, numerous paradoxes arise if backwards time travel were possible, suggesting cosmic censorship against changes to the past. Rather than materializing from nothing, quantum particles like photons can seemingly travel backwards in time by taking strange paths through space-time allowed by quantum uncertainty. This raises mind-bending interpretations of free will, causality, and information loss in black holes. Chapter 11: The Forces of Nature. In his concluding chapter, Hawking reiterates the quest to unify all the forces of nature into a single grand framework. He reviews progress in formulating a quantum theory of gravity necessary to understand conditions at the origin of the universe during the Planck era. The extreme energies required to experimentally probe systems at the Planck scale make this a speculative, theoretical endeavor. Hawking remains optimistic that integrating general relativity's geometric model of gravity with quantum field theories can lead to a unified theory of everything. He reiterates how the evolution of the universe can be understood scientifically, from the spontaneous quantum fluctuation that sparked the Big Bang to the fundamental laws of nature that govern particles and spheres propagating through the space-time continuum. Deriving this unified physical theory is the ultimate goal of physics, which Hawking believes philosophers and other thinkers must support to understand reality at its deepest level. Conclusion. In this popular science classic, Stephen Hawking skillfully conveys core insights from relativity, quantum theory, and cosmology to general audiences. He covers profound concepts like warp, space-time, black holes, the Big Bang, the expanding universe, and the arrow of time with wit, passion, and intellectual rigor. The central lesson is that the universe operates rationally according to elegant mathematical principles which physics seek to discover through empirical observations and theoretical advances. Hawking argues that anyone can grasp how modern physics reveals humanity's place in a universe with a definite beginning that will likely continue expanding indefinitely absent some unforeseen cosmic catastrophe. He dispels mysticism by showing that the cosmos is knowable through reason, science, mathematics, and bounded only by our imagination and skepticism of perceived common sense. Hawking ends with a call to unify gravity with the other forces through a quantum theory of space-time whose predictions can be experimentally tested. By making the universe less mystifying, Hawking celebrates our capacity to collectively unravel its deepest truths through rational inquiry without recourse to mysticism or pseudoscience.